Welcome, everyone. It's exciting to be here. This is certainly not my first participation in this meeting, and hopefully for many of you that's true as well. I'm a computer scientist. I know very little about neuroscience, and I work predominantly in high-performance computing. For me, what's been fascinating about this meeting as a scientist is to learn about neuroscience. I mean, they're just these wonderful aha moments that I get from some of the talks at this meeting. But from what I'm paid to do, the value to me of coming to this meeting is the ideas that it sparks about how we can leverage insights from neural systems as we think about the future of advanced computer systems. So let me start by just acknowledging that we live in very exciting times. So the BRAIN initiative, of course, you all know about, has the potential to substantially increase our understanding of how brains work. As we'll hear more about, there are large programs around the world now that are committed to exactly this question. Within the States, there's something known as the National Strategic Computing Initiative. I actually mentioned this to you guys last year, that it was in the works. It actually got announced this summer. It's all of government is the language, so a multi-agency commitment to advancing computing in several frontiers. And a very important element of the National Strategic Computing Initiative is that it includes non-traditional approaches to computing. Things like quantum computing, neuromorphic computing, non-traditional, non-CMOS electronics, with an intent of trying to figure out what we do as a computing community and how we consume computing after the end of Moore's Law. So we've had this wonderful run of exponential performance improvements for decades now, but that's not going to continue for that much longer. Within the Department of Energy, where I work, in one of the national laboratories, there is an Exascale initiative. An Exascale project is being stood up with a push to attain performance of 10 to the 18th. So the 18th is exa, operations per second on very, very large scale machines. It's a very daunting challenge. The goal is to get there by the mid-2020s. I think that there will be other nations that probably do stunts at this scale prior to that, but the DOE's goal is to do this in a way that's sustainable and moves an entire ecosystem forward in a very constructive way. There's Exascale, as I mentioned, is very challenging. There was a report done by a number of luminaries in the field articulating the top 10 challenges in getting to Exascale. And as you'll see from the list that I've excerpted from their report, many of the challenges are things that brains do extraordinarily well. So power is the overriding single most challenging impediment to getting to this scale with our traditional computing approaches. And basically this report concluded that they really didn't see a good answer for this problem. So we're likely to, at the 10 exascale level, at the exascale level, the first exascale computers will probably consume order 30 megawatts of power, which is really an amazing amount of power that very, very few facilities can actually countenance. Resilience, of course, is another big issue. Our traditional computing models are extremely fragile to errors, unlike brains. So these machines, in part to address power, in part to address performance, are going to very complex memory hierarchies. And questions about how we manage those, what the structure should be, both physically and conceptually, are things perhaps we can learn from brains. And then networking, of course, connecting the millions or tens of millions of processing units that we'll have in these machines. Somehow the brain does that in an amazing way. So CMOS, which is the technology that we build our current computing technologies out of largely, just can't shrink very much further. And ultimately that's what's going to limit, that's what's going to bring Moore's Law to an end. And so maybe this will get us to a few exaflops, the basic approaches that we're used to, but I know of no one in the community who thinks it'll get us much beyond that. So if we're going to continue to strive for further advances in computing performance, we're going to need to be receptive to much more radical changes in the way we think about our advanced computers. And the hope, certainly my hope, is that insights from this community, from neuroscience, from our understanding of brains, can provide some ideas that can percolate into more mainstream computing communities in a way that advance and enable future exponential growth in computing capability. So here are just a few possible concepts. I've broken this into hardware versus algorithms. Of course, as you know, there's already a lot of algorithmic work that's inspired by some at least limited understanding of how neural systems work. So the deep learning work, of course, has been a big success, but it's clear from the training requirements in those applications that they're not functioning as effectively as brains. But algorithms inspired by neural systems obviously can do machine learning. We know that well. They could also potentially manage these complex memory hierarchies as we learn how the brain manages those itself. They could monitor the state of a machine to recognize errors or detect errors or enhance resilience in various ways. And of course, looking for data analysis. Those are things that we know brains, and even some of our existing algorithms already inspired by brains already do reasonably well. More interesting to me is how insights from neural systems could inspire architecture and computer hardware. So the brain, as you all know, is an extraordinarily power-efficient entity, vastly superior to the way that our existing computers work. And so maybe there's something there that we need to understand. Well, there's a lot there that we need to understand better and potentially leverage. Neural-inspired devices could potentially provide fast matrix vector multiplication, power-efficient matrix vector multiplication, but probably at very low precision. There are algorithms you may hear about at this conference where neural models provide the opportunity to do certain things faster, provably faster than you can do in a traditional von Neumann model. Things like sorting, and we may hear more about that here. A somewhat ill-formed idea, neurons integrate. They integrate inputs and generate outputs. Maybe, just possibly, we could view our traditional scientific computations, instead of being differential equations, represent them in the integral equation form, and maybe hardware inspired by neurons could directly integrate those. I don't know, but I think we need to be open to ideas. So, to me, there are several next steps that are required here. Very, very importantly to me is we need better theoretical models of neural-inspired computing approaches. So the complexity models that we have for traditional computing have been deeply empowering in the way we think about algorithms, the way we devise algorithms, the way we implement algorithms. I don't think, certainly I haven't seen a similarly advanced model of the way we think about neurosystems, and I think modeling is really important. A question that's of keen interest to me, and I'll be listening to the talks this week, trying to elucidate insights into this, is which neural-inspired concepts are the ones that are really important? So I don't think hemoglobin and glucose are the important things, but is it spike trains? Is it asynchrony? Is it the co-mingling of processing and memory? Is it the connectivity structure? I've heard various opinions on these questions, and I welcome more. But as far as best I can tell, this isn't really a resolved question, and I think that understanding that will be really important as we move to abstract these concepts into more mainstream computing approaches. And then, of course, to enable all this, we need cross-community fertilization. And this meeting is a wonderful exemplar of that kind of cross-dialogue. But the communities involved, computing and neuroscience, they have very different scientific objectives, different vocabularies, different ways of thinking of the world, different definitions of what success is. And it'll require a lot of work to break down barriers and actually build these opportunities. But I think that the potential is so vast that I'm very eager to see this move forward. So with that, I'll turn the podium over to one of my colleagues, and we can continue the conversation.